have contravariant components. What I am saying is, if you understand it in terms of vectors and one forms, you don't require contravariant vectors or covariant vectors. Because contravariant vectors are vectors, covariant vectors are one forms. So there is no requirement of that language at all. Okay, so you simply have vectors. One forms have covariant components. So you can simply call them as one forms. And this is what in quantum mechanics you have ket vectors, kets, and this is raw vectors. And this is same as direct lattice vectors in crystallography, direct lattice, and this is reciprocal lattice.
So can we call it as a Fourier basis?
Yes, in a particular context, this will be if this is a coordinate basis, this will be momentum basis. Yes, in some sense you can. Essentially, the basis is different, but so what I'm saying is you have a vector space for which you can choose coordinate basis as the basis of this vector space, and then for this vector space conjugately you will take momentum basis, so then it becomes a Fourier basis. In the sense of but you have to be a little bit careful because you have to have what is called, so if you say this is your x basis, coordinate basis, then you must choose. Reciprocal basis is not a Fourier basis anytime, because we require this also to be an x prime such that x prime x becomes this Dirac measure, so x minus x prime. If I take a p here, then px becomes e power I kx. So it's not, it's another basis, but it's not the, so Fourier basis is not the reciprocal basis. Yeah, sorry.
So is it one form of vectors? Vectors are covariant among vectors. Vectors are covariant among vectors.
One form.
Therefore, we should write vectors. The second line. Vectors.
So maybe I should not write it like this. I should write contravariant vectors, as we know in the books, are simply vectors. Covariant vectors, as we know, are one forms. Okay, so this is the kind of connection that we have for, and the vectors. Vector, you put a metric tensor here, you get the one form. And you get a vector by taking the inverse of the metric tensor. So metric tensor will transform the inverse, will transform vectors to one forms to vectors. In other words, metric tensor will transform contravariant to covariant vectors, contravariant components to covariant components, covariant components to contravariant components. And yeah, so that is the summary of the basic definitions of these vectors and tensors. So any questions, sir? I think we are now ready to do some physical examples, and we can consider some tensor quantities that we come across in physics, and then look at what kind of tensors are these in the light of definitions that we talk about. For example, you all might have heard of moment of inertia tensor. So what kind of tensor it is? What is its rank? It's second rank tensor. So what are inputs and what are outputs? So angular velocity and angular momentum are the inputs. So it's a 1, 1 tensor. Two vectors are inputs. So it's a 1, 1 tensor. These are two vectors. Okay, one can be considered as a one form. Okay, because you have to get what is called two vectors, angular velocity vector and angular. So what you write is L is equal to I omega. This is the usual vector equation we write. This is the moment of inertia tensor. So that means there is another category that when you say you have one, when can you get, suppose you have a box here and you are sending one vector and also getting another vector, right? It is something like this. It's a vector valued function of a vector variable. You are sending omega in and you are getting L out. So this is equivalent to saying that if I have, as I told you, that this 2, 0, 0, 2 and 1, 1, they are all equivalent, they are isomorphic to each other because they are all second rank tensors. So if I think that I have got a function of u and v, let's say I have a function of u comma v, okay, I can use, that is for a fixed value of u. If I fix u, then this is only a function of one vector variable. That means input is one vector, output is a scalar. So for a fixed u, I can always write f of u comma v using that fundamental theorem that I proved earlier, that this can be written as some a, which depends of course on u because I fixed u dot v. Because if I change u, my a also will change. So I can write a dot v. So the scalar can be obtained by a vector dot v. Okay, so it is like now what happens? This is 0, 2. Whereas this quantity is like one vector, and this is also. So what does this mean? Whenever we write a vector in the, so this also is a vector, right? So this is a vector. So this will be like a one form because I want to get a scalar. So this will be like a tilde of u dot v. So maybe I should simply write it as comma v. This should be a scalar. So this should be a one form. So I can write this as a one form. That means I have one form and one vector in this case. So this is 1, 1 type. right? This is 1, 1 type. Okay, so 0 to type can be written as 1, 1 type by using the fundamental theorem. So all these vectors that we come across in physics, the second rank tensors, may be inertia tensor or the polarization is equal to some susceptibility times the electric field, the linear polarization vector, or the current density is equal to sigma, the conductivity tensor times the electric field, and so on. So these physical tensors, they are all second rank tensors. So where two vectors are proportional to each other. Each component can be proportional to each other. Okay, so maybe we can just do one simple problem and understand how the tensorial nature of these physical quantities will give rise to some physical effects. Okay, so I will in particular try to show one particular, we will do momentum inertia tensor definitely, but before that I will try to show you how birefringence comes as a consequence of tensorial nature of the dielectric tensor. So your material's response to the applied electric field, if it is anisotropic, then your dielectric constant will be a tensor quantity, and the susceptibility will be a tensor quantity. So because of the tensorial nature of this, you have a property called birefringence. You send in a ray, the ray will split into ordinary ray and extraordinary ray. So this birefringence property is a consequence of the tensorial nature of the susceptibility of the dielectric response. So I will show you, demonstrate how that comes about later. We can stop here. Okay, so maybe after lunch I will show you that. I will show some physical examples